Hey everyone, my name is Amna and you're watching Amna Unfiltered. Today we're diving deep into the fascinating world of artificial intelligence to explore a topic that's stirring excitement and curiosity across the tech community. In this video, we are pitting two of the most talked about AI models against each other, DeepSeek v3 and GPT-3. As the AI landscape continues to evolve, these models stand at the forefront, pushing the boundaries of what machines can understand and achieve. Join me as we embark on a thrilling journey to decode these technological marvels, uncovering their secrets, capabilities, and how they're reshaping our digital world. The realm of artificial intelligence is no less than a battleground where titanic models like DeepSeek v3 and GPT-3 clash, each powered by billions of parameters and trained on vast swaths of data. These aren't just algorithms, they are behemoths designed to mimic human intelligence, understand languages, generate text, and even write poetry. But what makes them different? Why do these differences matter, and how do they impact us as users, developers, and citizens of a rapidly digitizing planet? These are some of the questions we'll be exploring today. Let's start by setting the stage with GPT-3, a name that has become almost synonymous with modern AI in public discourse. Developed by OpenAI, GPT-3 has been making waves with its 175 billion parameters that empower it to perform a wide array of tasks, from composing essays to solving coding challenges and even creating art. It's a model that has democratized AI in many ways, providing developers and creators with a tool of unprecedented power at their fingertips. But it's not just the capabilities that make GPT-3 a standout. It's the philosophy of open-ended design that allows it to learn from its mistakes and evolve through user interaction. Enter DeepSeek v3, the new contender, which takes a different approach with its mixture of experts architecture. This isn't just another AI model. It's a paradigm shift in how artificial intelligence systems are designed and deployed. With 671 billion parameters, DeepSeek v3 isn't playing the same game as GPT-3. It's playing a whole new game. Each expert within DeepSeek v3 is a master of a particular domain, be it language understanding, problem solving, or even creative writing. This model represents a leap towards more efficient, targeted, and adaptable AI systems, promising to enhance how we interact with technology. As we peel back the layers of these AI giants, we'll explore their training methods. Imagine training not just a machine, but an oracle that learns from every book, every article, every piece of digital text it can analyze. DeepSeek v3 was trained on 14.8 trillion tokens, a massive pool of knowledge that's been distilled into a model that can think, analyze, and create. GPT-3, while not trained on as many tokens, still benefits from a diverse and expansive data set, making it incredibly versatile and capable. But this video isn't just about understanding these models in isolation. We're here to compare, to challenge, and to critically analyze. How does GPT-3's uniform architecture stack up against DeepSeek 3's specialized experts? Can the generalist approach of GPT-3 outperform the targeted efficiency of DeepSeek 3 in real-world tasks? And beyond their capabilities, what about their impact? How are these models being used in industries, from healthcare to entertainment, from education to ethics? In our discussion, we'll also delve into the implications of such powerful technologies. With great power comes great responsibility. And as these models become more integrated into our daily lives, understanding their ethical dimensions, their potential for bias, their security risks, and their societal impacts is crucial. We're standing on the brink of a future where AI could either become an indispensable ally or a challenging force. Understanding these nuances is key to navigating the future we're building. So, buckle up as we embark on this intellectual adventure. Whether you're a tech enthusiast, keen to understand the latest in AI, a developer looking to leverage these technologies, or just a curious mind eager to see where the future of technology is headed, this video promises to provide deep insights, critical analysis, and a glimpse into the future of artificial intelligence. Stay tuned, engage with the content, ask questions, and let's unravel the complex, compelling world of DeepSeek v3 and GPT-3 together, right here on Amna Unfiltered. Architecture. In the realm of artificial intelligence, where innovation and advancement are the norms, the architecture of a model is the bedrock upon which its capabilities are built. It defines not just how the model operates, but also how it interacts with the vast arrays of data it processes, the efficiency with which it learns, and the breadth of its applicability in real-world scenarios. Among the leaders of this groundbreaking journey is DeepSeek v3, a model that stands out not just for its vast parameter count or its cutting-edge applications, but for its revolutionary architecture, the mixture of experts, MOE. Imagine a vast library, sprawling and diverse, filled with knowledge across all conceivable subjects. Now, imagine navigating this library not as a single individual, but as a team of specialized experts, each with deep knowledge in specific fields, efficiently finding and utilizing the exact resources needed for any given query. This is the principle behind the MOE architecture utilized in DeepSeek v3, a principle that allows a model to handle tasks not just with high proficiency, but with remarkable efficiency. At the core of DeepSeek's v3 architecture is the innovative use of multi-head latent attention, MLA, a sophisticated twist on the traditional attention mechanisms employed in earlier AI models. In traditional models, attention mechanisms help the system focus on relevant parts of the input data, but they do this uniformly without regard for the nature of the data or the specific requirements of the task at hand. True MLA changes this by introducing multiple heads in the attention mechanism, each capable of focusing on different aspects of the data, depending on the task. This not only improves the model's ability to handle complex data sets with nuances and subtleties, but also significantly enhances its processing speed and reduces computational overhead. At its core, we believe this is where we are going, and I think we're ready for the true testing to begin. Consider the implications of such an architecture in practical applications. In language translation, for example, MLA allows DeepSeek v3 to simultaneously focus on grammatical structure, cultural nuances, and contextual relevance, delivering translations that are not only accurate, but also contextually appropriate. In content creation, from writing articles to generating code, this architecture enables the model to focus on syntax, style, and logical flow all at once, producing results that are coherent, stylistically consistent, and logically sound. Moreover, DeepSeek v3's architecture is designed to be inherently flexible, allowing for easy scalability and adaptation. This flexibility is crucial in today's rapidly evolving digital landscape, where the demands on AI systems can change dramatically in short periods. The MOE architecture, with its segmented yet integrated experts, allows DeepSeek v3 to scale up or down based on the complexity of the task and the volume of data it needs to process. This scalability ensures that the model remains efficient and effective, whether it's processing millions of transactions in a high-speed trading platform or offering personalized recommendations in a streaming service. The auxiliary loss-free load balancing strategy employed in DeepSeek v3a architecture further underscores its innovative approach. In many large-scale AI models, balancing the computational load across different parts of the network can lead to inefficiencies, as the model spends valuable computational resources just managing how tasks are assigned and handled. DeepSeek v3's strategy eliminates this issue by using a dynamic routing algorithm that optimally assigns tasks to different experts based on real-time demands, ensuring that no part of the model is over or under accumulated. This not only enhances the model's overall efficiency, but also significantly improves its longevity and reduces the wear and tear on the physical infrastructure it runs on. Furthermore, the impact of such an architecture extends beyond mere computational efficiency. It has profound implications for energy consumption, a critical consideration in an era where the environmental impact of technology is increasingly scrutinized. By optimizing how tasks are assigned and processed, DeepSeek v3 minimizes unnecessary computation, which in turn reduces the energy required to run the model. This makes DeepSeek v3 not just a powerful tool for businesses and researchers, but also a more sustainable choice in the broader context of global technology use. In essence, the architecture of DeepSeek v3 is a reflection of the future of artificial intelligence. It embodies a shift from the brute force processing of earlier models to a more refined, intelligent approach that leverages specialization, efficiency, and adaptability. As we continue to push the boundaries of what AI can achieve, the principles embedded in DeepSeek v3 HI architecture provide a blueprint for building AI systems that are not only powerful, but also responsible and sustainable. Through this innovative architectural approach, DeepSeek v3 is not just processing data, it is paving the way for the next generation of AI systems that will drive the future of industry, technology, and society. But let me count. In the fascinating realm of artificial intelligence, the sheer number of parameters in models like DeepSeek v3 and GPT-3 is much more than a testament to technological muscle. It represents a profound leap in the quest for machines that can think, learn, and create like humans. Parameters, in the context of neural networks, are the fundamental elements that the models use to make predictions and decisions. They are the gears in the clockwork of AI, each adjustment and turn refining the model's ability to parse and understand the complex tapestry of human language and behavior. DeepSeek v3, with its staggering 671 billion parameters, stands as a colossus in this landscape. To comprehend the scale and impact of such a number, envision a city of neurons, each connected by myriad pathways, representing every conceivable aspect of human thought and culture. This vast network is not just large for the sake of size. Each parameter serves a purpose, contributing to the model's deep and nuanced understanding of data. The massive parameter count allows DeepSeek v3 to engage in highly complex computations, manage more extensive data sets, and achieve subtler nuances in tasks, ranging from language translation to content creation and even complex decision-making processes. The advantage of having such an immense number of parameters is akin to having a library at your disposal that contains every book ever written. Whenever DeepSeek v3 encounters a question or a problem, it can pull from this vast reservoir of knowledge, ensuring that its responses and solutions are well-informed and deeply considered. This capability is particularly crucial when handling tasks that require a deep understanding of context, subtlety, and complexity, such as interpreting legal documents, crafting literary works, or conducting technical analyses. Conversely, GPT-3, developed by OpenAI, boasts 175 billion parameters, a figure that, while dwarfed by DeepSeek v3, remains profoundly significant. GPT-3's architecture allows it to perform a broad range of tasks with remarkable proficiency. This model has democratized AI, providing developers, researchers, and businesses access to high-level AI functionalities without the need to develop such complex systems in-house. The difference in parameter count between DeepSeek v3 and GPT-3 underscores varied approaches to AI development. DeepSeek v3's larger parameter count is indicative of a model designed to delve deeper into the nuances of data, providing more detailed and accurate outputs, especially in tasks that benefit from a deeper understanding. In contrast, GPT-3's relatively lower parameter count emphasizes efficiency and versatility, making it suitable for a wide array of applications where speed and broad understanding are prioritized over extreme depth. The impact of these parameter counts extends beyond technical capabilities. In terms of learning and adaptation, more parameters mean a model can learn from more examples and fine-tune its responses to be more accurate and contextually relevant. This learning process is critical for applications in dynamic environments, where the context and requirements can shift rapidly, such as in financial markets analysis, real-time interactive systems for customer service, and adaptive content generation systems that respond to user feedback. Moreover, the training of such large models is an endeavor that pushes the boundaries of current computing capabilities. Training DeepSeek Web3, for instance, involves massive data sets, extensive computational resources, and a significant amount of time. Each parameter needs to be adjusted through numerous iterations of training, with the model learning from every interaction to refine its algorithms and improve its accuracy. However, the benefits of this extensive training are manifold. For industries reliant on precise and reliable data interpretation, such as healthcare and pharmaceuticals, the depth and accuracy provided by DeepSeek v3 can lead to breakthroughs in drug discovery and disease diagnosis. For sectors like entertainment and marketing, the creative capabilities of these AI models can transform content creation processes, offering personalized and engaging user experiences. In summary, while the parameter counts of DeepSeek v3 and GPT-3 highlight the sheer scale of these models, their real value lies in how these parameters are utilized to foster understanding, generate insights, and solve problems across various domains. As we continue to navigate the complexities of AI development, the thoughtful application of such extensive computational resources will remain a cornerstone of innovation, driving forward the capabilities of AI to understand and interact with the world in ways that were once the realm of science fiction. Training data. In the ever-evolving landscape of artificial intelligence, the breadth and diversity of training data are as crucial as the architectural nuances and the computational power of the models themselves. Training data is the foundation upon which AI models such as DeepSeek and GPT-3 build their understanding of the world. This data not only teaches them about language, logic, and facts, but also imbues them with the nuanced understanding necessary to interact with human users in meaningful ways. As we delve into the specifics of the training data for DeepSeek and GPT-3, we explore how each data set contributes uniquely to the capabilities and performance of these groundbreaking models. DeepSeek, a behemoth in the realm of AI, has been trained on a staggering 14.8 trillion tokens. This colossal number isn't just for show. It reflects a profound commitment to creating an AI that understands and processes information with an unprecedented level of complexity and subtlety. Since each token in this vast data set represents a piece of information, a word, a number, a piece of punctuation that contributes to the model's experience and knowledge. The scale of DeepSeek's training data allows it to detect patterns and learn nuances that would be imperceptible with smaller data sets. Imagine trying to understand the entire scope of human culture, language, and knowledge. Now imagine trying to compress that understanding into a machine. This is the challenge that DeepSeek's training dataset rises to meet. It includes a myriad of texts sourced from a diverse array of domains: literature, scientific articles, popular media, technical manuals, historical texts, and more. Each domain enriches DeepSeek's knowledge base, enabling it to perform well across various tasks, whether it's writing a poem, summarizing a complex medical article, or generating a user-friendly explanation of a quantum physics concept. The diversity of the dataset not only bolsters the model's general capabilities, but also ensures its proficiency across specialized tasks that require deep domain knowledge. On the other hand, GPT-3 by OpenAI, though trained on fewer tokens, still utilizes an extensive and diverse dataset culled from a broad sweep of the internet. This includes books, websites, and other forms of text, offering a rich tapestry of human thought and culture. GPT-3's dataset is designed to mirror the vast array of information available online, providing it with a balanced understanding of both formal and informal registers, technical and layman terminologies, and objective and subjective forms of writing. While not as large as DeepSeek's dataset in terms of token count, GPT-3's training data is comprehensive enough to make it one of the most versatile AIs on the market, capable of generating human-like text that is contextually relevant and engaging. The implications of these training data sets extend far beyond the ability of these models to generate text. For instance, the depth and diversity of DeepSeek's training data enable it to engage in few-shot learning, where the model can deliver high-quality responses even with minimal user input. This is because the extensive training allows the model to fill in the blanks effectively, drawing on its vast internalized knowledge to make educated guesses about what information the user is seeking. Moreover, the quality of the training data directly impacts the ethical dimension of AI deployment. Models trained on diverse and well-curated datasets are less likely to perpetuate biases and inaccuracies. For DeepSeek and GPT-3, careful dataset construction and management mean that both models are better equipped to handle sensitive topics with the needed nuance and care, reducing the risk of generating harmful or biased content. Training such advanced models also poses significant technical challenges, particularly in terms of data management and processing. The infrastructure required to store, manage, and process trillions of tokens efficiently is monumental. It involves not only massive storage solutions, but also powerful processing algorithms capable of handling enormous throughput without loss of data integrity or processing accuracy. In conclusion, the training datasets of DeepSeek and GPT-3 are much more than mere collections of texts. They are carefully constructed ecosystems of knowledge that define the abilities of these AI models. They ensure that the models are not only technically proficient, but also culturally and contextually aware, capable of interacting with as we continue to push the boundaries of what AI can achieve. The thoughtful curation and expansion of these data sets will remain a critical factor in the evolution of intelligent systems, shaping the future of how machines learn about and understand our world. Inference efficiency. In the realm of cutting-edge artificial intelligence, the efficiency of a model during the inference phase is pivotal, as it directly influences the model's practical application and utility in real-world scenarios. This efficiency determines how quickly and effectively an AI can respond to queries and perform tasks, making it a crucial aspect for users who rely on real-time or near real-time AI assistance. DeepSeek v3 and GPT-3, two of the most advanced AI models currently in use, showcase distinct approaches to optimizing inference efficiency, each leveraging different architectural innovations to enhance their performance. DeepSeek v3, with its sophisticated mixture of experts architecture, represents a significant departure from traditional neural network designs. This model is not just built to be large or powerful, but smart in its operational dynamics, particularly during the inference process. The MoE framework allows DeepSeek v3 to engage only the necessary parts of its neural network, the relevant experts, based on the specific demands of the task at hand. This selective activation is akin to a surgical team, where each member has a specific role and is only called upon when their particular expertise is required. For example, if the task involves language translation, only the experts trained specifically in linguistic structures and language nuances are activated, leaving other parts of the network dormant. This approach not only speeds up the inference process, but also reduces the computational load, ensuring that resources are not wasted on unnecessary operations. The selective activation of experts during inference allows DeepSeek v3 to handle complex, multifaceted tasks more efficiently than if every parameter were engaged each time. It reduces latency, saves energy, and crucially allows for scalability. As tasks vary in complexity, the model can dynamically adjust which and how many experts to engage without the need for additional computational overhead. This makes DeepSeek v3 highly adaptable and capable of operating efficiently across a wide range of devices, from high-power servers to more constrained devices like smartphones and embedded systems. On the other hand, GPT-3, developed by OpenAI, employs a more traditional dense architecture. While this model is also highly efficient, it operates under a different paradigm, where the entire network is utilized for each task. This approach ensures that GPT-3 benefits from the full range of its learned capabilities on every operation, which can be advantageous for generating high-quality, contextually rich outputs. However, utilizing the entire network means that GPT-3 often consumes more resources per task than a model with an MoE architecture. For every query processed, every layer and node of GPT-3's vast neural network is activated, drawing substantial computational power and potentially increasing the response time, especially for more complex queries. This difference in approach highlights a fundamental trade-off between comprehensiveness and specialized efficiency. GPT-3's all-encompassing activation provides a robustness to its responses, making it highly effective for tasks requiring deep contextual understanding, however, this can also lead to inefficiencies, particularly in situations where the computational cost is a critical factor, or the tasks do not require the full might of the model's capabilities. Moreover, the inference efficiency of each model influences its applicability in different environments. DeepSeek v3's MoE architecture makes it particularly suitable for environments where varying tasks of differing complexities must be handled rapidly and concurrently. This could range from real-time interactive systems, such as digital personal assistants, to complex analytical platforms used in research and development. In contrast, GPT-3's dense architecture might be more suited to environments where the depth and quality of each response are paramount, and computational resources are less of a constraint, such as dedicated AI systems for content creation or customer service chatbots designed to provide detailed, informative, and contextually appropriate. In essence, the inference efficiency of DeepSeek v3 and GPT-3 not only defines their operational effectiveness, but also shapes their potential use cases. As AI continues to integrate more deeply into various sectors of industry and daily life, the choice of architecture, whether more or dense, will play a crucial role in determining the suitability of a model for specific applications. This consideration is vital for developers, businesses, and end users alike, as it directly impacts the cost, speed, and utility of AI deployments in real-world scenarios. Learning strategies. In the intricate world of artificial intelligence, the strategic underpinnings of how a model learns not only illuminate its present capabilities, but also hint at its future potential. DeepSeek and GPT-3, two titans of the AI field, utilize distinctly different learning strategies that reflect their architectural philosophies and end goals. These strategies are not mere procedural choices. They are core to the model's operational essence, dictating everything from their efficiency and adaptability to how they evolve over time. DeepSeek, with its cutting-edge approach, employs auxiliary loss-free strategies for dynamic and efficient learning. This method marks a significant evolution in the training of neural networks, especially for a model as complex and layered as DeepSeek. Auxiliary losses, traditionally used in machine learning, are supplementary objectives that help in stabilizing and improving the learning process. However, they can sometimes lead to complications, such as slowing down the training process or leading the model to focus on the wrong features. DeepSeek's approach eliminates these potential pitfalls by removing auxiliary losses altogether, thus streamlining the learning process. This strategy ensures that DeepSeek learns directly and solely from the primary objective, enhancing both the speed and purity of the learning. The removal of auxiliary losses means that every bit of computational power and every data input is used to directly enhance the model's core capabilities without the distraction of secondary objectives. This approach not only makes DeepSeek highly efficient, but also allows for more straightforward fine-tuning and adaptability post-training, as the model isn't bogged down by the vestiges of auxiliary objectives. This auxiliary loss-free strategy aligns with DeepSeek's mixture of experts architecture, which optimizes the allocation of tasks to different expert components of the neural network. Each expert is fine-tuned for specific types of data or tasks, allowing DeepSeek to manage a vast array of challenges with remarkable agility and accuracy. The synergy between DeepSeek's learning strategy and its architectural design exemplifies a holistic approach to AI development, where every aspect of the model's design and operation is aligned to create a seamless, efficient learning machine. On the other hand, GPT-3's learning strategy takes a more traditional route, leveraging its vast array of parameters and extensive training datasets. Powered by a dense neural network architecture, GPT-3 undergoes a rigorous training regimen that involves processing enormous amounts of text data. This method, while resource entirely, allows GPT-3 to develop a broad and deep understanding of human language, making it incredibly versatile and capable of generating contextually rich and stylistically varied text. GPT-3's reliance on large-scale data and computing power is reflective of its foundational design philosophy, that more data and more processing lead to better, more nuanced AI. This approach has proven effective, enabling GPT-3 to perform a wide range of language tasks with a high degree of proficiency. However, it also means that GPT-3 requires substantial computational resources to train and operate, which can be a limiting factor in terms of accessibility and scalability. The contrasting learning strategies of DeepSeek and GPT-3 highlight a broader debate within the AI community about the best path to artificial general intelligence, AGI. Is it better to build highly specialized, efficient systems that learn with surgical precision, or should the focus be on creating versatile, general-purpose models that learn from as much data as possible? DeepSeek strategy suggests that efficiency and targeted learning can lead to powerful, adaptable systems that push the boundaries of what AI can achieve in specific domains. Meanwhile, GPT-3's approach underscores the value of versatility and broad knowledge, suggesting a model that can adapt to a wide variety of tasks and evolve over time with continuous exposure to new data. As AI continues to evolve, the learning strategies employed by models like DeepSeek and GPT-3 will not only determine their immediate effectiveness, but also shape their long-term impact on technology and society. Whether optimizing for efficiency or versatility, the ultimate goal remains the same: to develop intelligent systems that enhance human capabilities, foster innovation, and solve complex problems in ways that were previously unimaginable. In this quest, the learning strategies of today's AI models lay the groundwork for the transformative technologies of tomorrow. Fine-tuning capabilities. In the expansive domain of artificial intelligence, the process of fine-tuning a model is akin to sharpening a blade. It is an essential refinement that enhances the model's precision and adaptability, allowing it to excel in specific tasks beyond its general capabilities. This process is particularly significant in the context of DeepSeek and GPT-3, two advanced AI models that, while capable of impressive general performances, each possess unique fine-tuning capabilities that suit different types of applications. DeepSeek, with its innovative mixture of experts-more architecture, is engineered to thrive in environments requiring high specialization. Post its comprehensive pre-training phase, which equips it with a broad base of knowledge and capabilities, DeepSeek is specifically designed to undergo fine-tuning with smaller, task-specific. This capability is not just an added feature, it is central to the model's design philosophy, allowing it to adapt its vast array of expert components to highly specialized tasks with remarkable efficiency. Imagine DeepSeek as a well-displayed kitchen, with every possible gadget and ingredient at its disposal. The pre-training provides every tool and flavor you might need to create any dish in the world. The fine-tuning process, then, is like honing this kitchen's capabilities to master specific cuisines. For instance, if the model needs to excel in legal document analysis, fine-tuning would involve training it further on a targeted data set comprising legal texts, case studies, and judiciary documents. This not only sharpens its existing capabilities, but also aligns its vast resources specifically towards understanding legal terminology, logic, and implications. Much like a chef specializing in French cuisine would focus on techniques and ingredients pertinent to that style. The strength of DeepSeek's fine-tuning capability lies in its MOE architecture, which effectively allocates the learning task to the most relevant experts within the model. Each expert can be fine-tuned independently, enhancing the model's ability to not only learn, but also apply this learning in highly specialized contexts. This approach minimizes interference between unrelated tasks, ensuring that learning in one domain does not inadvertently dilute the model's capabilities in another. This makes DeepSeek extraordinarily versatile and precise in its specialization, capable of transitioning smoothly between tasks as diverse as medical diagnosis, financial forecasting, and creative writing, each with its own set of expertly fine-tuned parameters. On the other hand, GPT-3, developed by OpenAI, also possesses the capability to be fine-tuned, albeit with a different architectural approach. Unlike DeepSeek, GPT-3 utilizes a dense, transformer-based architecture that, while incredibly powerful, does not inherently segment its processing to specialized experts. This architecture lends itself well to a broad range of applications, benefiting from a vast training dataset that enables the model to generate highly nuanced and contextually rich content. However, when it comes to fine-tuning for highly specialized tasks, GPT-3's flexibility is somewhat less pronounced than that of Mo-based models like DeepSeek. GPT-3 can certainly be fine-tuned to improve its performance on specific tasks, but this process generally involves adjusting the entire model slightly towards the desired application. This could mean retraining the model on a new data set that includes examples of the specialized task. However, because the model's architecture is not segmented into experts, this fine-tuning can sometimes lead to compromises in other areas of performance. For instance, enhancing GPT-3's ability to write medical research papers through fine-tuning might inadvertently affect its ability to perform well in writing fiction, as the nuances required for each are vastly different. This difference in fine-tuning flexibility can significantly impact the choice of model depending on the intended application. For industries and tasks where highly specialized knowledge is crucial and must be regularly updated or modified, DeepSeek's MoE architecture offers a distinct advantage. In contrast, for applications requiring broad capabilities and general adaptability, GPT-3's dense architecture might be preferable. In conclusion, the fine-tuning capabilities of DeepSeek and GPT-3 highlight a fundamental aspect of modern AI development: the balance between generalization and specialization. As AI continues to evolve and integrate more deeply into various sectors, the ability of models to adapt and excel in highly specialized tasks will become increasingly important. This will not only enhance the model's effectiveness, but also extend their applicability, enabling more personalized, accurate, and efficient AI-driven solutions across all spheres of human activity. Performance in specific tasks. When discussing the performance of artificial intelligence models in specific tasks, the architectural nuances of each model play a crucial role in determining their effectiveness. DeepSeek and GPT-3, two formidable AI systems, showcase distinct strengths that cater to different types of challenges, reflecting the diversity and specialization inherent in modern AI development. DeepSeek, with its innovative mixture of experts architecture, is particularly adept at handling tasks that require highly specialized processing. This specialization is a result of the model's ability to dynamically engage only the relevant portions of its vast network, tailored to specific tasks. Each expert within the model is fine-tuned for a distinct type of data or problem-solving scenario, enabling DeepSeek to approach complex challenges not just with brute force, but with a refined strategy akin to a skilled craftsman wielding the perfect tool for each detail. Consider, for example, a task involving the analysis of medical imaging. DeepSeek can activate its neural network experts that specialize in visual data and those knowledgeable about medical diagnostics. This targeted activation allows the model to interpret the nuances in medical images more effectively and provide insights that are both clinically relevant and highly accurate. Well, similarly, in tasks such as financial forecasting, experts trained to analyze numerical data and market trends can be mobilized to deliver precise predictions, demonstrating the model's capability to adapt its vast resources to the demands of highly specialized tasks. The MOE architecture also enables DeepSeek to maintain this high level of performance across a wide array of specialized tasks without compromise. Because each expert operates somewhat independently, the fine-tuning or learning of one group of experts doesn't detract from the capabilities of others. This means that DeepSeek can excel in multiple specialized tasks simultaneously, a significant advantage in environments where versatility and depth of knowledge are crucial. In contrast, GPT-3, developed by OpenAI, excels in tasks that require a broad understanding of language. This capability stems from its extensive training on a diverse range of internet text, encompassing everything from literature and technical manuals to GPT-3's dense transformer-based architecture processes this eclectic training data to develop a comprehensive understanding of language, enabling it to generate text that is contextually rich, stylistically varied, and often indistinguishable from that written by a human. The strength of GPT-3 shines in applications such as content creation, where it can seamlessly mimic various writing styles, or in conversational AI, where it can engage users with responses that are contextually appropriate and engaging. Its ability to draw upon a wide-ranging understanding of human language also makes it particularly useful in tasks such as translation or summarization, where nuances of meaning and context are paramount. However, the broad applicability of GPT-3 also means that it may not always reach the level of specialization that MOE models like DeepSeek achieve. While GPT-3 can adapt to a variety of tasks with considerable success, its single model approach may not always handle highly specialized tasks with the same level of precision as a model like DeepSeek, which explicitly allocates different parts of its network to become experts in narrowly defined fields. The contrasting performances of DeepSeek and GPT-3 in specific tasks underscore an important aspect of AI development: the trade-off between breadth and depth. While GPT-3 offers breadth, able to handle a wide array of tasks with competence, DeepSeek offers depth, excelling in areas that require specialized knowledge and processing. This distinction is crucial for organizations and developers when choosing an AI model, as the best choice depends heavily on the specific requirements and challenges at hand. In essence, the performance of DeepSeek and GPT-3 in specific tasks not only highlights their technological prowess, but also illustrates the broader strategies and compromises that shape modern AI systems. As the field of artificial intelligence continues to evolve, the balance between specialized and generalized capabilities remains a central theme, driving innovations that cater to an increasingly complex and diverse array of human needs. And whether it's through the lens of a specialized tool or a versatile all-rounder, the journey of AI is about enhancing our ability to understand, create, and make decisions. A journey that is as diverse as it is dynamic. Cost efficiency. In the realm of artificial intelligence, where technological prowess often measures success, the concept of cost efficiency plays a critical and often decisive role. It is the balance between computational demands and economic viability that can either propel an AI model to widespread adoption or confine it to the annals or of an experimental exercise. DeepSeek and GPT-3, two state-of-the-art AI models, illustrate contrasting approaches to managing cost efficiency during their training phases, each tailored to their unique architectures and operational goals. DeepSeek, with its innovative approach to machine learning, is particularly designed to optimize cost efficiency. This model harnesses the power of FP8 mixed precision training, a technique that allows it to perform computations with less numerical precision than traditional methods. This might sound minor, but the implications are profound. Lower precision means that each operation requires less computational power, less electricity, and less time, significantly reducing the cost of training without a substantial sacrifice in performance. Imagine a scenario where an AI model needs to learn from billions of data points. Using standard precision, this process could be likened to weighing gold with a highly sensitive scale that measures down to the last milligram. FP8 mixed precision in this metaphor would be akin to using a slightly less sensitive scale that might not catch the finest details, but is significantly faster and cheaper for bulk processing. Sure, for most tasks that DeepSeek undertakes, the level of precision offered by FP8 is more than adequate, allowing it to learn effectively and efficiently from vast data sets without incurring the prohibitive costs associated with higher precision levels. This strategic decision is not merely about cutting corners to save costs. It's about smart allocation of resources to optimize learning efficiency. By reducing the computational load, DeepSeek can be trained on larger data sets or for longer periods within the same budget constraints, enhancing its learning depth and breadth without additional costs. This approach also extends the lifespan of the hardware involved, as less intensive computation translates to less wear and tear on the physical components. Another aspect of cost efficiency. Furthermore, DeepSeek's mixture of experts make architecture complements its use of FP8 mixed precision. This architecture allows the model to activate only the relevant parts of its neural network during specific tasks, reducing the number of active computations at any given time. This selective processing not only speeds up individual tasks, but also reduces the overall inertial consumption and improves the model's runtime efficiency, key factors in lowering operational costs. On the other hand, GPT-3 developed by OpenAI showcases a different approach to cost efficiency. As a model that relies on a dense, uniform neural network architecture, GPT-3 requires significant computational resources to train. Its training involves processing vast amounts of data through all its network layers, a method that, while comprehensive, demands substantial energy and computational power. This approach can be costly, given the need for high-power GPUs that must operate continuously over extended periods to complete the training process. However, the trade-off here is the simplicity and robustness of deployment. Once trained, GPT-3's single model approach can be easily deployed across various platforms and applications without the need for significant reconfiguration or additional fine-tuning. This simplicity can reduce the long-term costs associated with deploying and maintaining AI systems, particularly in environments where versatility and general applicability are prized over highly specialized performance. The contrast in cost efficiency strategies between DeepSeek and GPT-3 highlights a fundamental aspect of AI development: the balance between immediate training costs and long-term operational efficiency. For potential users and developers, choosing between these models often comes down to evaluating specific needs against available resources. If the priority is to achieve high performance in specialized tasks with cost-level training, DeepSeek may offer the optimal solution. Conversely, if broad applicability and ease of deployment are paramount, despite higher initial training costs, GPT-3 could be more suitable. In essence, the narrative of cost efficiency in AI training is about much more than just saving money. It's about strategic resource management, technological sustainability, and long-term vision, ensuring that the development of AI models like DeepSeek and GPT-3 is not only a triumph of engineering, but also a viable component of our technological future. As AI continues to evolve, the principles of cost efficiency will remain central. guiding the development of models that are not only powerful and versatile, but also economically feasible and widely accessible. Scalability. In the vast and dynamic arena of artificial intelligence, scalability is not merely a feature, but a fundamental aspect that determines the extent to which an AI model can adapt and grow in response to varying demands. It is a critical characteristic that ensures AI models like DeepSeek and GPT-3 can be effectively utilized in different environments, from small-scale operations to large, complex systems. The way these models are designed to scale, their architectural backbone, and their inherent computational strategies dictate their ability to evolve and expand without compromising performance. DeepSeek, with its state-of-the-art mixture of experts HX architecture, brings a novel approach to scalability. This model is inherently designed to distribute tasks efficiently across its network of experts, each specialized in different domains or functions. This segmentation allows for a highly modular form of scalability, where individual components or experts of the model can be scaled independently according to specific needs. Imagine a vast assembly line where each station is not only capable of increasing its output independently, but can also adapt its function based on the demands of the moment. In practice, this means that DeepSeek can enhance its capabilities in specific areas, such as language understanding, image processing, or logical reasoning, without the need to scale the entire model uniformly. This targeted scalability is particularly beneficial in environments where computational resources are a limiting factor, as it allows for precise adjustments to the model structure to meet specific demands without extensive overhead. The flexibility of DeepSeek's MOE architecture significantly enhances its operational efficiency. For example, if a new task requires enhanced image recognition capabilities, only the experts specialized in visual processing need to be scaled up or further developed. This modular approach not only conserves resources, but also speeds up the adaptation process, as changes are confined to relevant areas, reducing the complexity and risk associated with large-scale modifications. On the other hand, GPT-3, known for its dense, transformer-based architecture, follows a different path towards scalability. The scalability of GPT-3 primarily involves increasing the depth and breadth of its neural network, adding more layers and parameters. This method, while straightforward, leads to a significant increase in computational demands and resources. Each additional layer or parameter set expands the model's ability to process and generate complex responses. But it also requires more data, more processing power, and more energy. In practical terms, scaling GPT-3 to handle larger or more complex tasks could be likened to powering up a giant machine. The more you expand its capabilities, the more fuel it requires. This approach to scalability is effective in environments where the depth of contextual understanding and response generation is crucial, and where the infrastructure can support large-scale computational loads. However, it poses challenges in terms of efficiency, cost, and flexibility, particularly when rapid or frequent scaling is necessary. The contrasting approaches to scalability between DeepSeek and GPT-3 highlight a fundamental divergence in AI development philosophies. DeepSeek's MOE architecture offers a more nuanced, flexible approach, allowing it to respond dynamically to changing requirements without the need for uniformly scaling the entire model. This approach is particularly well-suited for applications in dynamic environments, where different tasks may surge in priority at different times. GPT-3's approach, while less flexible, provides robustness and depth, making it ideal for applications where a deep, broad understanding of complex contexts is needed consistently. As AI continues to permeate various sectors, from healthcare and education to finance and creative industries, the ability of models to scale effectively becomes increasingly critical. Scalability affects not only the operational efficiency and economic viability of AI implementations, but also their ability to innovate and adapt to new challenges. In this light, the scalability of AI models like DeepSeek and GPT-3 is not just a technical issue, but a strategic one that impacts their long-term utility and success. In conclusion, as we advance further into the age of artificial intelligence, the scalability of models like DeepSeek and GPT-3 will continue to play a pivotal role in shaping their trajectories. Whether it's through the modular, expert-driven scalability of DeepSeek or the robust, layer-driven approach of GPT-3, understanding and optimizing these models for scalable growth will remain at the forefront of AI research and application, ensuring that these technologies not only meet the needs of the present, but are also primed for the unknown demands of the future, ethical and safety considerations. In the rapidly evolving landscape of artificial intelligence, the ethical and safety considerations of deploying such powerful technologies are becoming as crucial as their technical capabilities. With AI models like DeepSeek and GPT-3 pushing the boundaries of what machines can understand and accomplish, the potential for both positive impact and misuse grows. The Commission made a fine point that gender does not gate users. It gives a very lowering perception of what a machine is. How these models are managed, monitored, and modified plays a significant role in safeguarding the integrity of their applications and ensuring they contribute positively to society. DeepSeek, with its impressive capabilities, fueled by the mixture of experts' architecture, presents unique challenges and opportunities in terms of ethics and safety. Its open source nature is a double-edged sword. While it democratizes access to cutting-edge technology, it also opens the door for potential misuse by malicious actors. However, the transparency inherent in open source projects allows for broader scrutiny from the global community of developers, ethicists, and concerned citizens. This collective oversight can lead to quicker identification of flaws or biases in the model, facilitating timely modifications to mitigate risks. Imagine a world where every tweak, adjustment, and improvement made to DeepSeek is visible and accessible to all. This level of transparency not only fosters trust, but also encourages a collaborative approach to ethical AI development. Researchers and developers from diverse backgrounds can contribute their insights and expertise, helping to ensure that DeepSeek adheres to ethical norms and is resistant to manipulations. Moreover, the community-driven nature of open source projects can accelerate the pace at which safety measures are developed and implemented, as the collective wisdom and experience of the community serve as a robust defense against potential threats. The ethical implications of DeepSeek's capabilities, particularly in terms of privacy, fairness, and accountability, are profound. Given its ability to process and generate content at an unprecedented scale, ensuring that DeepSeek does not inadvertently perpetuate biases present in its training data is paramount. The community can play a critical role here, continuously auditing and refining the model to uphold ethical standards. Furthermore, the potential for DeepSeek to influence public opinion, policy, and personal decisions through generated content places a significant responsibility on its maintainers to safeguard its use, ensuring it promotes truth and fairness. On the other hand, GPT-3, developed by OpenAI, operates within a more controlled framework. OpenAI has implemented stringent usage policies to mitigate risks associated with the model's deployment. These policies are designed to prevent misuse, such as generating misleading information or creating harmful content. However, the relatively close nature of GPT-3's development can limit the ability of external parties to audit or assess the model independently. This restriction can slow down the detection of potential issues, as fewer eyes are examining the inner workings and outputs of the model. The challenge with GPT-3's approach lies in balancing control with transparency. While keeping some aspects of the model's development under wraps can protect against misuse, it also reduces the number of stakeholders who can contribute to its ethical and safe development. Unlike DeepSeek, where an open-source framework invites widespread participation and oversight, GPT-3's closed system relies heavily on internal checks and balances. Ensuring these internal mechanisms are robust enough to handle the ethical dilemmas posed by such a powerful tool is critical. In both cases, the importance of developing robust ethical guidelines and safety protocols cannot be overstressed. As AI technologies continue to permeate various aspects of human life, from legal systems and healthcare to education and entertainment, the potential for them to impact lives for better or worse increases. For AI models like DeepSeek and GPT-3, crafting these guidelines and protocols means looking beyond the immediate applications and considering long-term implications, ensuring that these technologies are not only effective, but also equitable, safe, and beneficial. And in conclusion, while the technical prowess of AI models like DeepSeek and GPT-3 is undeniably impressive, their ethical and safety considerations are what will ultimately define their role in society. Whether through open source collaboration or controlled development environments, ensuring these models are used responsibly is essential as we forge ahead into a future increasingly shaped by artificial intelligence. The collective efforts of developers, users, and policymakers will be crucial in steering these powerful tools towards outcomes that are not only innovative, but also inclusive, ethical, and aligned with the broader goals of human society.